So problem 1. This is just like a warm-up problem. So find the number of subsets. Find the number of subsets of 1 to n, okay, with an even sum. Let's think about this. I had done a similar question in one of the previous videos, which I had suggested. But anyways, we can just think about this. So we want those subsets in which the sum is even. Maybe empty set will also count. Yes, that is what the sorry. Extremely sorry. Yeah, that is what the idea is, right? Because intuitively all of us understand that it should be the answer should be 2 to the power n minus 1, right? Even if you have not been in the previous classes, you know that the answer should be this. So the idea is to show a bijection. So how do we do it? Yeah, show a bijection between subsets so you guys can think how to do that, and subsets with odd sum. This was even a homework in that class, I think. But yeah, let's see. So we just want a natural way to pair up the elements. This power set, we want to pair up the elements in the power set. With even sum, we want to pair them with odd sum. Things like that. So first,
Also for these kind of questions,
taking modulo.
like here it is 2, that's why it's not divided.
No, no. What is 2? You mean even sum, this thing. Okay.
and it was like some like this yeah this can be generalized like minus limit of this here
Okay, good idea. Okay, I get the idea. Right. That's a good idea. That will be slightly non-bijective proof. I will expand on that after this problem, but that's a good idea. But can we do this by bijection first? Or anyway, we'll do, but let's do this problem first. No, because then you may, if n is there, then it will become n plus 1 if you're going to increase the greatest element. So this can be done non-bijectively. What Adish is saying with somewhat generalized can be done, can be used. But I just want to emphasize on this technique. You want a natural way to pair up the elements on this side to elements on this side. Because this technique is very powerful because you don't have to count anything, right? You would just know that these two sets have same size without actually counting, without actually knowing the size. That's a very powerful way to do problems. So the question really is, what is a natural way to pair up the elements? This might be a little unfair because you guys may have other solutions, but we're just trying to pick up this technique. And it does give a very neat solution. So that's the advantage. So you can ask yourself, what should I pair up 5? Hmm. Okay, right. So let's see. So yeah, so let me write that recipe. Maybe I just call it recipe. Given S, yeah, if one belongs to S, then return or just output S minus 1, else S union 1. Does everybody see why this will take a set with even sum to a set with odd sum? Like clearly, because the sum is changing by 1. Okay, why is it the bijection? I mean, it's obvious, but still. Right, I think that's a very good way to say it, right? It has a good inverse. So if you call this process F, then what is F inverse? It is just basically F again. it has the same inverse. That is that is a good thing, right? And we understand what f is, right? F takes, for example, so f will this way, it will take 5 to 1. It will take 2 comma 4 to, so where will it take this? Right. And you see in this way, and then it's a self bijection, because when you apply f on this again, you can, because the way we have defined f, you can apply it on any subset. You actually go back to the same thing. So it's a self inverse. So it's done, right? Now the sets of same size, and so it's this is the exact same technique as we had done number of subsets with even size, and here it's even sum. Okay, but sometimes it could be more complicated, and then you may have a tough time to directly counting that it is 2 to the power n minus 1, because you see, you may have seen a lot of complicated identities whose answer is 2 to the power n minus 1, right? So if you do it non-bijectively, and if you do it by dividing into cases or taking modulo, then you may actually end up solving a huge identity in the end by algebra or whatever. Okay, so this can save all that work, and it has a lot of other significance you will see later. So this was fairly simple. Let us now just discuss as a somewhat what Adish was saying, I think. So Adish, can you do you have a idea of how can you do this problem in a slightly different way, or if anyone has, then we can build on that. So this is not the focus of the class, but it's a good thing to know or see, and maybe some new ideas will come which I have not thought of. Non-bijective way, like you were saying something about taking modulo, so maybe as a hint, like taking the numbers modulo 2 might help. Right, so if I take modulo 2,
So it's a even if the sum of that is short but
yeah, this encoding, this directly encoding like this will not help, because you kind of lose a lot of things. But yeah, induction will work. Yeah, induction is like recurrence basically. Yeah, induction will work. Let's not use induction, but yeah, induction will certainly work, and it should not be very difficult. Yeah,
I was actually talking about the technique will work.
no, but then it should work for 2 also.
This is not making like this will work, but it is not.
But how will it work? Let's first see how will it work.
This technique is working, then we can just
No, no, no. But to be honest, we have to first see how to make it use it for 2, right? Then you can extend it the same way. When is the sum even? When is the sum of a subset even? That is right. Yes, right. Yeah. Yes. Yeah. So basically, you can just look at this only. This maybe is not going to work because we are just losing a lot of information, and I don't know how that you can make it work. But this, if you just look at this, then sum is even when you have, as you said, even number of odd numbers. Yeah, when even number of odds, right? So you can just, yeah. So you can just do a casework on number of odds, right? You can just do simple casework, and it's very say inductive casework. So casework, yeah, but that will be the same exact same thing. Yeah, as we have done bijective. But you can just do casework. You can just say one. Yeah, it's kind of splitting the problem into parts which are easy to count. Right, right. Divide and rule, you can say, yes. Okay. So it is very simple. If you take zero odds, then you can see, then basically all evens. So you have to see the number of evens. How many even numbers are there? N by 2. And then you have to do casework on n is even or n is odd. And 2 to the power n minus n by 2 or something, right? Subsets with only evens. Yeah, and then you can do one odd. And you don't even have to do further casework on the size. I'm saying this roughly, but you understand, right? You don't have to do casework on the size, on the rest of the size, right? You have to just do one odd. Now, if it's one odd, then you have to, from the odd numbers, let's say n by 2 odd numbers, if n is even, n by 2 choose 1. So it will be this times the rest is just, you can take any subset from the evens, right? You see, and then two odds, and you do n by 2 choose 2, and again same thing. And in this way you can do, you see. So it's actually not very difficult if you split it in the right way. And then again, if it's like find the number of subsets with sum 3k plus 1, then again you understand you have to do casework in this way. Okay, so let me give that as a problem, and you guys can also think of a bijective proof of that as well. That will be a good way to do learn this. Okay, so let's not erase this. Let's keep this here. You can have a look at it. So S is, so I'm just keeping a general n. You can do your casework and tell me what the answer is. S is this. It's a good calculation to do. Don't just leave it at the level of ideas. You have to do the calculations and then it will be useful. S is this. So find number of subsets with sum 3k plus 1. So let's see how you do it. You can do it by this way, and you can also do it by bijection. Both the methods will become slightly more complicated, but see how you can manage. Try it. Okay, try it. So note this down. Okay. So now I want to, so this is one of the extensions of one of the problems we had done earlier. I want to now go into extensions of another problem which we had visited earlier. So I'm erasing this. You can see it later also. So a problem about paths returning to origin. So it's a simple way to state a problem which can be said in many ways about paths returning to origin. We had this was a problem that someone had just naturally come up with, one of you only, I think, and when we were trying variations of path countings. So this is the problem. You want to, so you have this thing, first of all, it's coordinate axis, and then you want to count, first of all you have some number of steps. Okay, you can Just use these things. Sorry. Let me first write the problem, right? Yeah. So path starting at origin. Okay. And the moves that you are allowed at each step, moves at each step is up, down, just unit moves, up, what is happening? Up, down, north and east. These are the moves. And number of moves, well, I can just give anything, but yeah. So the number of moves is 2n. You can see why that is. And path returns to origin. So at the 2nth step, you must return to the origin. You can return before, in between also. But at the 2nth step, you must definitely return. If in between you return, then you have to again move and so on. Okay. So yeah. So how many such paths are, yeah, how many such paths? So this is again, let's see. Think about this. As some of you may have already thought about this. We had seen this earlier. That's right. Yes, that is exactly what that's the entire problem, right? West and up, down. Yes, obviously. Yeah, sorry. So up, down. So it should be west and east. Just say left and right because it's up and down. Yeah. So before I'll just give an example so that it's very clear for everyone what exactly the problem is. So just an example is um, like this first step, then up, then you can go up, then you can come back, come down, again you can go, again you can go, you can take the same thing again and come down, right? So you see, this is how I'm following: left, down, down, left, up, right, down, back to the origin. How many steps will it take? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 steps. So n equal to 5. So this is just an example. Okay. Now let us see. Okay, yeah. So let x be number of hops. And this was the technique that we had used to solve many other simple questions like this. Let's see. Be number of hops. Y Y is number of lefts, right? And then x plus y must be n. You see what x plus y is n because number of downs is also x, right? Number of ups has to be equal to number of downs, and number of lefts has to be equal to number of rights. And that is exactly same as coming back to the origin. Like if that happens, then you will come back to the origin. It's correct both ways. And similarly. Right. So what do we do now? 2n factorial. Okay, can you explain us why we are doing this? Square. Yeah. Mm-hmm. Uh-huh. Okay. Right. Does everybody get this so fast? Okay. Because if you look at this example, right, then it's just a sequence of rights and lefts. Here, this is just a simple encoding. Then you have rights and then up, up. If you follow the path that I've drawn, left, then you have down, down, left, up, right, down. You see this. And so you will have to look at the number. So this is a sequence of length 2n, okay? And x things are of one kind, okay? That x is the number of ups. So these things are of one kind. And then other x things are of another kind. And similarly, you see one copy of y things are of one kind and another y things downs. Sorry. Yes. Right. But you see that it's yes, that's right. But there is still more to do here because x and y are varying. Okay, we don't know the exact number of x and y. Right. You see, so x and y are varying. So this will depend on the number. You may not use any, you may not go up at all. Right. So this is where the problem is longer, slightly longer, not difficult. So it will be summation and you can just say, yeah, x is going from 0 to, actually, yeah, it can go from 0 to n. And why this condition is there. So we can write it or anything. Okay. Now I'm changing the x. Yeah. No, that is right. Yeah, that's right. So basically, depending on the number of ups, and that will decide everything else. That is key. So this is a rather boring way in some sense, right? A little boring way to do this question, especially when we finish this, we will see. There's something very interesting still remaining in this question, I think. So now just try to find the final answer. Meanwhile, yeah, it is. I'm just removing the question. I think we know the question very well. So anybody has found the final answer? Yes, right. So the final answer, and you guys can do this. I think it will be this. This is not difficult, just some summation. 2n choose n whole square. Interesting, isn't it? Very simple answer. And this, I'm not doing this, why this is coming. This you can do. Just do it. So if you can't do, then we can discuss. But this suggests something, right? 2n choose n times 2n choose n. It means that this, we have done the problem in a harder way than we are supposed to. So what do you think should be the next question, right? The next question is to find a bijective proof. Okay. Now again, you can see it just as fun and more elegant, but maybe that can be a question, but it's also very, it will say something deep if you can find a direct bijection. But bijection with what? So here is number of paths returning to origin. Origin into n steps. And we want to set up a bijection of this with this number 2n choose n square. Now what is 2n choose n square? Anybody can say that in terms of paths, because if you're going to build a bijection, first thing we look at is paths, right? Can you think of a path counting type problem which has this as the answer? Going from 0 to 0 to n, but not one path, pair of paths. Right, okay. So this will be number of, that's right, yeah, 2n choose n is the number of, so all of us know this 2n choose n is the number of paths from 0, 0 to n, n, when the moves are right and up. The usual game, the usual thing that we know, the first path counting problem that you do. So this is number of pairs of paths. So somehow this problem has two paths encoded somehow, and we have to bring that out directly, not just on the level of numbers that they're equal, fine, I got the answer, but on a, just, physically something is, yeah, they are connected. So number of pairs of paths, P1 and ordered pairs, obviously, P2 from going from 0, 0 to n, n. Now this bijective proof, I've never seen a bijective proof of this problem. Okay, I did have an idea last time, but that time I didn't get a time to finish it. I didn't get a time to get into it. Okay, so maybe that sounds better, right? Somehow more related to the problem. So let's use that. Number of paths, number of pairs of paths, p1 comma p2, which are respectively, they are 0 comma 0. No. So they will be of the same length. In some sense, they are shortest because, but the moves are right and up, so they are all the same length. Yeah, yeah. But yeah, if you introduce, if you say 4 moves, then this is shortest path, right? That's a good observation. And then P2 is path that comes back. But yeah, it's the same thing, but it just gives a more better decoration to the set, which maybe can help us to think. So I'm erasing these numbers now. Now they are not very important. Not important, maybe. I don't know. Let's see. Mm. Uh, yeah, but that is the same. Yeah, that will also have the same answer. You're perfectly correct. But this seems to be better tuned with the question, right? One path going to then comma n and simultaneously the other coming back, right? You feel that, right? Because of the nature of the problem. Yes, that's why. Otherwise, I can also say, a number of n size subsets, but that doesn't seem like, I mean, obviously there can be a bijection, there can be a natural, obviously there is a bijection because the size is same, but there can be a natural bijection, but that seems to be more far-fetched. But I don't know. Yeah, there can be probably. Let's see. I have to also think. Yeah. So you have to create pairs of paths. Maybe we can think for this case also only. Given this path, how do you create from here? How do you associate to this a pair of paths? Oh, yeah. Yeah, this diagram is very light. Or I can just make this dark. Okay. Okay. So let me write what you have said first. So use you're saying use the R and use to go up, right? Use the R and use to, yeah, okay, yeah, that's better. That's right. Sorry. Yeah. 0, comma 0 to n, comma n. Uh, but will I be able to go using the R and the use? Can you explain us? But maybe, yeah, yeah. Yeah, I just write that as like this. This is n, right? Yes. Yeah, seems like this will not work. Yeah, this will not work. In this direct way, it will not work. So you have n, so r plus u is n, total number of r's and total number of u's is n. And this is also equal to total number of l's plus total number of downs. This is also n. Mm-hmm. Uh-huh. Okay. First, you're going right in this. Um, just give me 1 second. Let me make you draw the grid first, right? Quickly. So wait. So this is how many was 10, right? So I'll have to go to 5, comma 5. 1, 2, 3, 4. Will be better, right? Yeah. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3. Sorry. This. this Yes, this is a complete, yeah. Okay. So this is the 5 by 5 grid. This is 5, comma 5. Okay, so yeah, now Adish, you were saying, I think, yeah. Okay, okay, okay. So here is 0, comma 0, and here is 5, comma 5. Let me shift this. Yeah, so you guys think, I'm just, hmm, what? Yeah, the usual move. So that is right and left, sorry, right and up for P1. And since P2 is coming down, you can say down and left, right? So in P1, so this is the usual paths. So P1 is right and up, and P2, well, it's also right and up, but if you're coming down, then it's like down and left. They can intersect and whatever, they can do anything. So an example would be you take this path going up, and then you can take a path which comes down like this. Maybe they can also intersect, doesn't matter. And we want to count, basically both are paths from 0, comma 0 to n, comma n with the usual usual moves though. But yeah, you can see it as returning also. So we need to create this kind of path, this pair of path. We want to create one pair of path from this diagram or from this sequence. How do you go? So you need, if you want to create path that goes from the origin to 5 comma 5, you need 5 rights and 5 ups. Here you don't have that. But number of rights and ups is 5 and number of lefts and downs is also 5. Mm-hmm.
Like for left, you should consider right side. And while coming down, the that's
No, you should not take the reverse path. If you take the reverse path, then you won't get all pairs of paths. Or maybe you're saying something else. You want to have possibilities for all pairs of paths. But let me note down what you said first. I think that was so. Can you say? I think what was the first way you said? Once, yeah, yeah.
like we consider
Okay, so just give me 1 second. Let me say then this, that number of rights and ups is 5 and number of lefts and downs. Wait, is this correct? Yeah, that is correct, right? Yeah, this is 5. So if you're making P1 by you saying right and left, both right move, both are corresponding to right move. This is what you're saying.
yes sir.
But this is not good.
Objective is to get 5 rights.
But then you won't get 5 rights. If you consider rights and lefts to be both right, then you won't get 5 rights because R plus L is not 5.
And also like the information like going left is also
Is not there in P1? Yeah,
at the information is also
yeah, that might be, but that you may recover in the returning back path. But the main thing is that you won't go to 5 comma 5 because our number of rights and number of L's and number of lefts don't add up to 5. But L's into ups and downs into rights. Yeah, so that was the same problem, right? As what Adish said. Okay, so can you say that again, maybe more precisely? So if you send the downs to right, no, you should send the ups to right, if you want to get 5 rights in P1. Oh, so that must also, right. That's right. Yeah, but if it's the same, then let me just then you can say it in a more straightforward way. That's right. So you can just say that yeah, that will also work, and probably that's what you have to do for the returning back path. But for the natural thing, we can just say that um, the D's that you are doing, we can make that right, and the right remains right. Okay, and the no, not yeah, or I will first say up. Let the ups because then it will be more clear from the what we have written. Okay, yeah, and make the yeah, but there will be problems either way. Make the lefts as ups and make the downs also as ups. Right, and then no, we are starting from the origin and doing this. No, no, it will be clear because you have this, right? You have a path which returns back to the origin. And from there, we will unambiguously create a path from 0, 0 to 5, 5. And right? No, no, we will not cross because you see, the number of rights and ups will be 5. Is 5, right? Is 5. The number of rights and ups is 5. So now the number of rights totally will become 5 in the new path. That is the reason why we're doing this. That's right. Yeah. So then let's make it. So R remains R. So we are making P1. So pay attention. We're making P1. Okay. R remains R. Up becomes R. Okay. That is what we have written here. And that's simply just to make it 5. You can think of it like that. I'm sure there is a better explanation. There should be. But it seems to work. Yeah. It won't be, but it will be, you see, if because there's a pair of paths. Yeah, you are thinking that information is getting deleted, but you see, we are adding another coordinate in the range that will. So this up will be right. Okay, and the left is up. The left is the new up. So when we see left here, we go up, and when we see down also we go up, and again we go up, and again we see left, so we go up, and then we go right. Wait, so how come 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So how come it's going one extra? Yes, yes, even I didn't understand. So I don't know what happened. Let's do it according to what we have written. Then that's why that's why I knew something like this. Yeah. So it's the height is a problem. Yeah, obviously 1, 2, 3, 4. So it will always be a problem. Yeah, because this is drawn in a very bad way. Oh. Yes, 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 yeah. Now we should, and you can understand. You have to just do. You have to make sure you use all the. Yeah, or you can just take this. You can just take a path from 0, 0 to n, n again. Okay, and just use it. Just use the information in the other way. Yeah, same thing. Yeah, just see we. So yeah, you are right. You'll get it. Yeah, just use it in the other way. Okay, so first, okay, right. So I'll say that it will be clear that it's a bijection. First, is it clear to everyone how P1 is constructed? I want no one to be unclear about that. Okay, it's clear, right? Okay. So, and this, don't try to, it's nothing to remember here. Okay, it is just a natural thing. Right? We are trying to get a path from 0, 0 to 5, 5. Okay. And so what two things add to 5? What other two things add to 5? No, one set we make right, another set we make up. Now, so just for simplicity, let me change this. Let me just change this to once again 0, 0 to 5, 5. Okay, so one path we got like this. Now let us think about how to make P2. Okay. So some of you may have got the idea by symmetry or otherwise, but let's try to say it in a way that it will be clear that all the information is present in the pair of paths. So here in the original path, we had rights and ups, and we had rights and lefts, and both rights and lefts are um, 5 in number, and no, the sorry, ups and that I made some, yeah, so it is here, sorry. Yeah. So the number of ups and rights was 5, and so we said, okay, let's keep the rights to be rights, and let's make the ups also rights. Okay, so the rights remain rights and the up also becomes right. So this basically this becomes R, 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 and the L becomes the up, and the down also becomes up, 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 and then U is R. Who's it happening? The U is R and the R is R and the D is up. This is what it is, right? So then this is wrong, right? This is, sorry, let me just give me 1 minute.
Go correctly.
Was it correct?
1, 2, 3. 2, 3, 4.
Mm-hmm.
Then 1, 2 here and
No, I didn't make another up. Yeah, I need to make another up. I just shifted the diagram and I didn't make it. Yeah. Yes, that's this. Yeah, this is what we get. Now, how should we make P2? Okay, so what I was going to say is we have lost we have lost the distinctness of R and U's. Okay, and we have lost the distinctness between L's and D's. Okay, we have identified R's and U's. Okay, so now you guys can think and tell me how to make P2.
that's why I that we should replace these by R. That's direct using.
So you can now do that in P2, right? You can do that for P2, right? So you can say, maybe you can say keep R to be R and make the D's R's. Is that right? So because we also know that the number of ups and number of downs is same, and the number of rights and the number of lefts is same. So this time we'll make the downs to be also R, and then the up will remain up and L will become up. And this way you see we'll get a new path, but we're just doing the complement. Okay, we are kind of just doing the next other thing. So let's first see what path we get. So R remains R. So this is P2. Up remains up. L becomes up. D becomes R. D becomes R. L becomes up. Up remains up. Then R and R. You get the other path. So this is how you get your pair of paths. Okay. Now does it look injective? Right? It looks, and you can prove it. So you can very simply prove it. You can take a pair of paths and you can see the number of rights. Hmm? It happens, right? I thought that only the whiteboard gets shared. I did not know this. Okay. So yeah. So this okay, should we shift it down? This is okay. This is the usual way to make the maps injective by adding more coordinates in the range. Naturally speaking, you can understand. Show injectiveness and basically bijectiveness. Yeah. So given a pair of paths, how would you get this? Now it's very, very simple because you can just invert everything. But if you just show that you can invert, because I'm trying to say that given a pair of paths, you know the rules, so you can basically determine the number of R's and number of L's and the positions and everything, and number of ups and downs. It's basically the yellow path can be seen as going back, but yeah, it, yeah, it depends on how you see it.
Sir, if you want to go back, then make and then set D
You're right. Yes, right. Yes. So, but let's do the injectiveness quick. Just try to see more, right? Because maybe it's not very clear to everyone, and even maybe little me also. It seems correct, but let's try to show that it's injective. I'm just making it a little smaller. What is happening? It's out of control. Maybe I should use some writing tool. No, we have to prove it's subjective. You don't know, but you can just give an inverse. Just give an inverse. Give an inverse. Then both will be proved directly, right? Given a pair of paths, give a way to go back so that from that when you apply this process you come back to the same path. That is important. Just giving one some arbitrary inverse is not given inverse. Given a yes, but if you just give an inverse then you don't have to do any of that. Like so you understand, right? So like I'm just saying that if you have a function f and you want to show that f is injective and surjective, if you can find a g, okay, so if right. Yes, so it will be like a both-sided inverse. So what I'm saying is that given a pair of paths, you have to give away so that you get back to you get a path which goes from the origin to the origin, but also the path that you get when you apply this original process, you must get back the same pair of paths that you started with. Okay, so it's not enough that this is identity. You should also have that this is identity. Both both the directions it should be working. Okay. Anyways, let's just think combinatorially and try to first go back. So suppose, for example, if I gave you two paths from origin from 0, 0 to 5, 5, right? Then how would you use them? So this is one path, this is P1. Let's say that if this was P1, so I'm just taking a different example so that, and if you just take another example, like this. Then using these two, how would you make your how would you make a naturally a path which goes from origin to origin? Which path? I didn't understand. Only if the original path was a left. Okay, okay, okay. Yes, yes, right. So you can just compare. Yeah, that's right. That's right. So let's go term by term and see. Yes, right. So if both of them are right, okay, what does it mean? So if this is right, then what are the possibilities? It means that in the original path, this first position, so let's write here original path. You can see that going through both checks will give you the exact thing. In the original path, what could have been this? If you just see, say we forget about this. If you just see this R, then the original path, you could have a up or a right, okay? But then you go to the second path and see, here is also a right, which means that in the original path, it was either a down or a right. But if both the statements are correct, it has to be a right. Okay, so it means it was a right. In this way, you can find uniquely, you can find everything. Okay, good. You've given the exact thing. Right. So this would mean up and so on and so on. You can understand. Up and right is down. Yes. Yes, because from down it's coming. Yeah, so this thing, the order is mattering, you see. Sorry, I was wrong. So this is down. Yeah. And in this way, you see, you can get back the path. And then you can apply and it's exactly the opposite. You can just show. This is rather unique. I have never seen this thing. Okay, but should be existing somewhere. I don't know. Okay. So this means that there are a lot of elementary and yet pretty interesting things that can be done in this area. Okay, and this is just an interesting problem that we have done. Yeah. So I think I'll just stop here today. I will give just one more question that you guys can think about, and if you just think about this also, if you need to, and maybe write a proof. This is interesting. Let's just give ourselves just 2 minutes of. I just want to think about something in this only. This is we have found it, but we just want to just I just want to have 2 minutes. So just yeah. Right. Okay. So anyone has questions? No questions. Okay then. So then we are done. I'll just give you one question that you can try. Because we just did pair of paths, we just suddenly came. But I considered pair of paths because I knew of this problem from before. But this is very different in some sense. Okay, but pair of paths appear here. So I knew that pair of paths are a combinatorially significant thing. Okay. So find the number of pair of paths from 0 comma 0 to n comma n such that, so pair of paths p1 comma p2 such that they don't intersect. Obviously, other than 0 comma 0 and n comma n that they meet, they don't intersect uh, during the journey or whatever. They don't intersect. Just you understand the question. They don't intersect. This can be done by casework maybe, but if you do by bijection, then it's better. Let's see. But I think this will become much more difficult to do by casework. That is the thing. Yeah. But yeah, yeah.
There it might be like many intersection
And which point? So maybe I don't know. First intersection, there's some recurrence, very complicated, very, very complicated. It can become. Yeah. But like Chandan once said, like intersecting at n comma n. So those variations are there, but this is much more complicated because you'll end up basically with inclusion exclusions, right? Intersecting at 2 points, 3 points, and then inclusion exclusion with summation over n squared terms and very, but it may still be a simple summation. I don't know, but yeah, just think. But yeah,
like it's related with bijection by
that is right. Yeah, that problem. Uh,
like not given.
Here it is not given. That's in some sense it is not given, but in some sense it is given. This is related, but we have not done that. Yeah, matrices is related with some matrices and number of walks on a graph, because a lattice is like a graph with certain edges, which edges are only those rights and ups, right? And those edges which are there, no diagonal. But yeah, we basically don't know. At this point, we don't know actually. We'll see. Think about this. Last time also when we were doing perfect matchings, I think I had mentioned the determinants can be used to count. Not determinants, there is something else, permanent. This can be done by determinants, but we will do by just very elementary bijections. You'll see. Okay. Okay then. See you next time. Hopefully we'll meet tomorrow. No, I think Thursday. Okay. We'll do calculus. Okay. Thank you.